Okay, so let me say a couple of words about the next homework. This assignment will be devoted to showing the only non-abelian simple group order less than or equal to 100 is A5. And it's like, oh my God, it's a concept album. This is bad, right? Well, I don't know, concept albums would be good, right? Is this Pink Floyd Wall or American Idiot, or is this music from the older by Kiss, right? Hopefully it was the former, not the latter. So this first question is pretty straightforward, but it will help you later. Suppose P and Q and R are distinct positive primes. Show that no group of order PQ is simple. Show that no group of order P squared Q is simple. And show that no group of order PQR is simple, right? These are all counting arguments. You can do these kind of counting things like we did with our first Sylow example. Number two, what we're going to do now is attack the case of a simple group of order 60. Number 2A is pretty easy. I really kind of broke this down into pretty small pieces. Find the possibility for the number of Sylow 2 groups and show that we only need to worry about 5 or 15 and trying to find a simple group of order 60. Show that if n is 5, then G is isomorphic to a subgroup of S5 and conclude that G must be isomorphic to A5. Number 3, show that if n is 15, so if you've got 15 2 subgroups, then there are 2 Sylow 2 subgroups called P and Q that must intersect in a subgroup of G of order 2. And number 3, if H is the normalizer in G of this intersection, show that 4 divides the order of H and that the order of H must be at least 12. And there's a hint with that one. And number E, show that since the index of H and G is less than or equal to 5, then G must be isomorphic to A5. So in those pieces, you put together that the only simple group of order 60 must be isomorphic to A5. 3 is a very kind of workaday problem. So use the previous and especially number 1 to make a list of all possible orders of G less than or equal to 100 and eliminate the possibilities except for 60 and 90, right? And because of A, B, and C, and also I didn't put this in A, B, and C in 1, but you also know that there can be no simple group of prime power order, right? P to the n. See if you can think, well, that's true. And you can eliminate, well, you can eliminate pretty much everything. There might be a couple of extra cases, right? You might have like PQR squared a couple of times, but you can deal with those on an individual basis and get down to these last 2. So that leaves 90, which I promised was kind of the hardest. And I'm going to do one that's a little bit harder than 90 today as an example. I show that the last one is assume that the order of G is 90 and suppose it's simple. This actually can happen, and we're going to show why that's true. Show that number 1, G is necessarily isomorphic to a subgroup. Well, I'm sorry. First, show that G must have 6 Sylow 5 groups. Simple. Number B, from that you can get that actually G must be a subgroup of S6, but do better than that. Show that it's necessarily isomorphic to a subgroup of A6. And finally, number C, derive a contradiction by showing that A6 has no subgroup order 90. Remember, A6 has what, 100, let's see, what's 6 factorial, right? That's 720, and well, so S6 has 720, so A6 has what, 360 elements. Show that it can't have a subgroup of order 90 by looking at, again, at group actions. Okay, any questions on that? So I wanted to throw this out here. This is, 1 should be easy, and actually most of 2 should be easy. You'll have to think a little bit about the last couple of parts. But this is, there's a long list here that you have to think about a little bit. I mean, it's not particularly hard. So I wanted to get this out there to you a little bit early and discuss it. Any questions? Okay, so let's pick up kind of where we left off. I talked, yes.
We will talk about middle exam, midterm exam.
Yes, it will be October 25th, on, which is a Monday, I think. And it'll be in class for whatever the class period is. By the way, let's see here. So what do I do with these guys? So the midterm exam, I will give you in class. I'll project it up there and you guys can look on your computer. I'll give you all, so here's my plan. I haven't really figured it out yet, but I plan to give you all an hour and then like a 5-minute grace period to take a picture of it and upload it. And I'll grade it just like it's a, you know, like a homework on the speed grader kind of thing. And so that's kind of the plan for that. But as we get closer, we'll figure it out. And we can have a review session too. If you think that'll be good for you guys, I'd be happy to do that. Right. Okay. So we were in the middle of the proofs of the Sylow theorems last time. And what we're proving now is this business about conjugation. So far, prove the first part. Last time, what we're trying to do is we're trying to prove the second one, which basically says if you have any P subgroup of G and you have a Sylow P subgroup of G, then you can conjugate that Sylow subgroup to make it contain the original P group. So let me review this real quick. Let S be the set of left cosets. P was our full Sylow P subgroup, and let H act on S. H is our P subgroup by left translation. That is to say, H acting on XP is H. Okay, now recall this was true actually for any group acting on set. Remember what S0 is. S0 is the set of all, in this case, left cosets that are left alone by everything. This was the equivalent to S mod P. And well, I know what the number of elements in S is because these are just the left cosets. In fact, this is an equality. So, right, because remember, the order of P A M with GCD and 1 and order of P A. So if you take this quotient here, it's M, right? And the quotient is M is not divisible by P. So what does that mean? Well, that means that P does not divide this, and therefore P does not divide S0, right? And so that means that S0 is not 0. Or I should say, the order of this, in fact, let me write something a little bit more explicit here. Let me just say, actually, it's bigger than this, right there. There's at least one thing in S0. So let's pick one of these cosets. Now this thing has to be left alone for everything in H. This means that H at P for all H and H. Right? That's what that action does. And hence, this means that X inverse HX, right? Because what this means is X inverse HX is still in P for every H and H. So that means that must be the case. And hence, I think what we can do is, I think, give my statement. Okay, any questions on that? Let me add to this as well. So what we've shown at this point is that any P subgroup is contained in the conjugate of given any P subgroup and any Sylow P subgroup, you can conjugate that, you can kind of twist it a little bit to contain H. So in particular, if H itself is another Sylow P subgroup, then we get that they must be conjugate. Right? So you could have arbitrarily picked H to be some other Sylow P subgroup called Q, and you get that Q is contained in these two, and you get an equality if the orders of H and P are the same. Okay, any questions on that? Okay, the last one actually is probably my favorite, because it's the one that's really most down and dirty about being able to count this, right? The last part of the statement says that if you want to count the number of Sylow P subgroups, call it N, then N must be equivalent to 1 minus P. And in fact, N also must divide this N here. So, the number of Sylow P subgroups and let's call it N. Is equal to the number of conjugates. Of any one. So I'm going to call one of my Sylow P subgroups P, and the number of Sylow P subgroups must be, since they're all conjugate, it must be the number of distinct conjugates of P. Right? So how do we now count that? This should be the index of the normalizer in G of P of G. You'll see why that's true. Right? Because if G acts on set conjugates, of P by computation. Once again, Rome's action. So again, G acts on one of these conjugates. Let this conjugate again. Then length of orbit is index of stabilizer. Or let's say of P, because you can take the orbit of any one of them, since they're all conjugate, there's only one orbit. Length of orbit of P is the nights of P is the index of the stabilizer, and the stabilizer is right, because this is everything in G conjugates D to itself. That's the stabilizer. Right. Like all that. So number of conjugates of P is and this number divides the order. Because the order of G is this thing times the order of the normalizer. This is a small observation here that this number divides G, but I'm gonna use it at the moment. Okay. Under this action, and S is the conjugates. In a Sylow P subgroup Q, okay, so let Q be an S. Remember, so Q is an arbitrary Sylow P subgroup. G, Q is in then Q then if Q is an S, then Q is an S naught if and only if so Q is an S naught, that is, it's preserved by all conjugates of everything in G, if and only if any conjugate of Q is Q itself. And so what does this mean? Well, this means that oh yeah, actually I want to up the stakes on this. This would, of course, be the Q is normal. So let's adjust this set here. Let S be set. So I'm sort of breaking with this original explanation of why the number is this index here. Let S be the set of Sylow P subgroups. And this is the same thing as the conjugates of G. Conjugates of P. And we were going to let P on this. So I'm not going to let the full group here. It's going to give you some insight to actually restrict my actions, not just letting the whole group. Certainly, the whole group acts on this by conjugation, but now I'm going to just let P act on it. So let's kind of go through this again. So if Q is a Q Sylow subgroup, if and only if well, it's P, correct? And this holds if and only if P because this holds if and only if everything in P conjugates Q to itself, which means that everything in P normalizes Q, right? Yes.
Can you remind me what S naught is?
S naught, for any group action on a set S naught is the stuff that's left alone by everything that the acting group does, right? So in this case, Q is S naught. To live in S naught, what this means is any action of anything on P must leave Q alone. So Q is in S naught if and only if P is in the normalizer in G of Q. No. Q is normal in the normalizer in G. I mean, after all, that's what the normalizer essentially does. It's the largest subgroup of P, on which this is the largest subgroup of G, in which Q itself is normal. So Q must be P, right? Because P is contained in the normalizer. Q is normal in there, right? So P and Q have to be the same. So what do we get from this? Well, so from this, that's it, right? Only so what we proved is that Q is in S naught and Q must be P. So P is the only thing in S0. And of course, since it's P acting on S, certainly P, we get the other containment, right? Because since it's P acting on the set of conjugates, whenever I conjugate P by anything in P, it's still in there. So I know that S naught at least has to have this in here. And if you've got anything else, it has to be P. So S naught is precisely P. And so since well, what is the cardinality of S? S is the number of Sylow P subgroups n. And S0 we proved is just the one subgroup P. And there we go. So n is equal to 1 plus xp. And n must divide the order of G. And the order of G is P to the A m. Right? Now, n and P to the A are relatively prime. And no factor in common because the only factors that P to the A have are P, and they clearly it's relatively prime to n because this is this form. Therefore, n must divide n as well. Because these two factors, P to the A and m, are relatively prime, and so since n divides the product, it has to divide the thing that's not relatively prime. Any questions on that? Yes.
Could you explain us once more about like how Q becomes P in the last step?
Right. So Q is normal, right? And what that means is, so that means that, P must be contained in the normalizer in G of Q. Well, so where do we get this? So we have Q here. This is in S0. So that means that it is frozen by everything in P, right? And we know that Q is normal in the normalizer here, a normalizer in G of Q. And we know that P is contained in here. Oh, right. And also P and Q are the same size. That's important, right? Because they're both aboard PPA.
Actually, does it have to be N of P? I'm not sure. Because we're only using elements in P to conjugate Q, right?
Well, yeah, that's true, but this is true more generally because remember what these all come from. These are all the conjugates in G. So the original set itself are all the conjugates, right? Because if it's only in P, you're not really doing anything because P itself, when you conjugate it by P, is trivially always P. So what you're looking at is you're looking at the complete list of conjugates as you range over all the elements of G, right? So it's P and it's GP and G inverses. You go through G. Now you let you let P act on this set. Now P clearly stabilizes P itself, right? Because now you're acting only by elements of P. But it's not clear it stabilizes the other ones, right? It might move those around. And so in this analysis here, we have Q being something that happens to be stabilized, right? So that means that P is contained in the normalizer in Q. So all P normalizes this, but Q is normal in this as well, right? And P and Q are the same size, right? Because it's important here that they're both Sylow P subgroups, right? Okay. How about a more sophisticated? So let me ask you this as well. Did you all understand the examples that we went through last time when we were doing the counting and all this? Let me give you one that's got a little bit more oomph to it. Example. Show there no simple order. Sometimes these problems get fairly difficult when you have many prime divisors and or when one of the prime divisors has higher and higher powers to a point. Okay, so let me use my notation again. Let's look at the possibilities here. Well, remember my notation is N2 is the number of Sylow 2 groups, and N7 is the number of Sylow 7 groups. This is equivalent to 1 mod 2 and divides 7. So I've only got two things that divide 7, 1 and 7, and these are both possibilities. N7 is equivalent to 1 mod 7 and divides 16. So I get some possibilities here. I get 1. Actually, I'm going to throw some out here. Now, of these, which are equivalent to 1 mod 7, 1 is, and 8 is, and the rest of them are not. Right. Now, let me, do you all see why this perhaps evades the usual kind of counting arguments that we had before?
mean large?
Well, right, so if it's simple, you have to have 7 two groups, and you have to have 8, you gotta have 8, 7 groups, right? Let's suppose we have 8 7 groups. Well, if we have 8 7 groups, that accounts for 48 elements of order 7. Everybody agree with that? Because every one of the groups has 6 elements of order 7, 48. Now you got the identity, 49. Well, no, let's not take it. Let's just go with the 48. So how many elements does this leave left over? You've got 64 elements, right? And you may say, well, that seems to be too big for this, but maybe not, right? Because the Sylow 16 group is, well, it's order 16, so it's got a lot of possible subgroups. Even if you've got 7 of those things floating around, that doesn't mean that you have a full complement of elements here, right? You don't have like, 15 times 7 or whatever plus 1. They can intersect in all kinds of exotic ways, right? So counting is difficult. I agree with that. Okay, so where do we go from here? Well, I am going to focus on Sylow 2 subgroup. And the reason is 7 is smaller than 8. It's going to be easier for me to work with. So let me make the observation that if E is simple, then N2 is equal to 7. Correct. So, well, let's let S be this is the set of Sylow 2 subgroups. There's 7 of them, right? Let G act on S by conjugation. And this induces a homomorphism. We'll call it phi into S7. Now, can anybody explain what makes this example a little bit more complicated than the ones that we were dealing with earlier?
Now P can be injected.
That's right. With a lot of these examples that I had before, then I said, oh, look, you got a group of order 72 going into a group of order 24. And I said, oh, look, the kernel can't be the identity. The kernel certainly could be the identity here, right? Because this only has 72 elements. I'm sorry, 112 elements, and this has 5,040. Right? What a mess, right? So, I mean, after all, there's no reason to expect this can't be injected. Right? Maybe it is. But let me go ahead and observe this. The kernel P is either the identity or G. Agreed? Got to be one of those two. Because we're assuming that G is simple, right? Let me add that there to the board parenthesis. Okay, so I'm going to throw out the kernel of the G is impossible. Somebody tell me why.
Then there should be only one
G, PI, G inverse equals PI. And this is a contradiction. I like your remark about the normality. That would of course mean that every Sylow group is normal, but this is only possible if there's only one of them. And very similar to that. Remember, all the Sylow subgroups are conjugate. We just proved that. And this statement right here says that I can't ever conjugate PI to anything other than PI. All right, so, okay, that can happen. Everybody cool with that? So, we conclude the is one-to-one. Its kernel is the identity. So I'm going to be a little sloppy with my notation probably. So G is identified with a subgroup. And when we say simple subgroup, of S7 of order 1. Everybody read that? So there must be, if there's a simple group, the conclusion, here's where we're at right now. If there's a simple group, there must be a simple subgroup of S7 of order 112. We may have actually proved this in class, but I can't remember when we actually proved it. The only
So this means G is isomorphic to the unit of by G to the unit of.
that is correct. That's right. So G is isomorphic to the image in S7, which is what we'll call PG, but instead of writing PG every time, only slightly, it's called G. So G is a subgroup of S7 or 112. Okay. Let me get the stakes here. I claim G is actually a subgroup of A7, not just S7. Anybody know how we do that? Consider. G intercept A7. This must be normal in G. Right? Because A7 is normal in S7, and G is a subgroup of S7. We had that old problem that if you have H is a subgroup of G and N is a normal subgroup of G, then H intersect N is a normal subgroup of H, right? This is a subgroup, right? Because anything that's in both G and A7, if you conjugate anything in G by G, it's still in G. And if you conjugate anything in A7 by something in G, it's still in A7 because A7 is normal, right? Okay. So, G intersect A7 must be either 1 or G. Because again, and since that's a normal subgroup, it's got to be one of those two. What happens in this case? This case is ridiculous. Do I know why? Yeah, any non-identity element but any non-identity element of G intersection of everyone agree with that? Because anything in G that's even ends up in A7. So if this intersection is 1, that means that everything in G, with the exception of the identity, is an odd element, right? Since the order of G is 112, select X, Y, such that X and Y are not equal 1. Pick any two non-identity elements. Notice that X squared because X squared is even. So it's an A7 and it's in G by hypothesis, right? And so is XY. Because X and Y are both odd, so X times Y is even. And since X and Y are both in G, so is XY. Agree? So X squared is 1, and that's the same as XY, right? Because since they're in A and A7 intersect G, it's 1. Therefore, X equals Y. So the order of G is less than or equal to contradiction. Okay, so this can't happen. It can't be the case, the intersection of G and A7. A7 in certain sense is kind of too dense. In fact, it's very hard to get interesting subgroups that are of this ilk in any symmetric group. Because when you square anything, you have to be in the alternate. Therefore, G intersect A7 is G. Therefore, G is a subgroup of A7 as claimed. Now, to finish this off, the order of A7 is whatever it is, 25, 1, 2 cubed, right? And that's 305, I guess. So it's 5. I guess that's 25.
Yeah, that's.
Right. Oh,
One more two. No, it's a cut. Yeah, that looks like.
and your G 112, which is 2, 4. So the order of G, not 5, or 97. Right. Notice I got away with something because it was precarious, but 2 to the 4 saves me actually here because S7 only has 2 to the 4th power in it. So when I go to A7, it pulls out 1 factor 2. It doesn't divide it. Okay, any questions on that?
I have a question. So the first contradiction, that means the conjugation action is trivial. So for any I from 1 to 7, the conjugate of PI is equal to PI. Why we get a contradiction here?
because of the Sylow theorems. The Sylow theorems say, given any two of these, you can conjugate them, right? So given P1 and P2, there's something that conjugates P1 and P2, any pair. But this says that all the PIs are left alone. That's impossible. Sylow theorem says this can't happen.
So they couldn't contribute with them, with themselves.
They can conjugate themselves, but what this says is they can only conjugate themselves, right? And the Sylow theorem said if you have any two of these, PI and PJ, there is some G that conjugates PI to PJ. But this one says that all G's conjugate PI to itself, and that's what contradicts the Sylow. Other questions? Okay, let me ask y'all something. How many of you have ever done anything with semidirect products? How many of you have heard of that? Okay, so let's kind of get both rolling on this one here. Now we have the Sylow theorem. This is, as you may expect, a generalization of direct products. With G and H groups. And let's say I call this theta from H into off G, a homomorphism. I think of this as sort of a fancy, more general way to conjugate things, because what I'm doing is, okay, I've got a pair of groups. Let phi from G and let theta be a homomorphism from H, input H, output is an automorphism of G. By the way, these kinds of things always bothered me when I was a student, but such a thing always exists. For example, you could have everything in H go to the identity automorphism. You could do that kind of silliness. And in fact, that's actually an important part of this. So let me do this first bit as a theorem. I'll do this way. Let G and H be groups. And theta, a homomorphism from H into all G. Then the set cross H endowed with the operation. So I'm going to tell you how to multiply things, so to speak. GH G1 H1 is, well, let me do the second coordinate first. Okay, I did the second coordinate just like I would do in something like a direct product. But I do something a little fancy in the first one. First coordinate, I'm going to let G, well, it's sort of like G times G1, right? But not quite, because I'm just not happy with myself unless I do something really kind of screwy here. And I'm going to do that. This forms group. Singular. Sometimes written as theta H homomorphs. And I can't remember whether it's this way or backwards, so I'm gonna look at it for it this time. But this is called the semidirect product. Now, this is really weird, isn't it, right? Because what we do is we multiply the second coordinate just like regular. And the first coordinate is, well, for the first coordinate, I need something in G, right? Because this is the set G problem. This needs to be in G. What have I done? I've taken G, that's in G. And then I've taken G1 and I put a little spice on it. And how did I put a little spice on it? Well, notice theta H is actually an automorphism of G. So this is an automorphism acting on G. So this turns us into something other than G1 perhaps, but still in G. That's what we get. This doesn't even look associated, does it? Right? I mean, but it turns out it is. Ask yourself this for next time. What happens when theta is the trivial homomorphism that takes everything in H to the identity? And you'll probably get something from that. Okay, we'll talk more about this next time. Any questions? How about out there? Everybody okay? All right. Well, you guys take care of yourselves and we will see you on Friday.